All right, do I have a volunteer that wants to start at the top of page 12? All right, if not, it says the simplest organic compound that has a double bond is ethene, which has a formula of C2H4. If we go back to our molecular packet up here, you can see that right there. The reason it's called ethene is because that eth, keep in mind E is the second vowel, that means it has two carbons, just like ethane, we talked about in the boiling point of activity, has two carbons. And the fact that it doesn't end in ane, but ends in ene, means it has that double bond there. And that's the question Jaden was asking about. The fact that it has two bonds means it's a double bond. It says here carbon still has four bonds. The double bond counts as two, and despite being a simple compound, ethylene is very important. It is a plant hormone that is responsible for promoting the ripening of fruit. If apples, for example, aren't stored with appropriate ventilation, the ethylene gas they produce will build up and cause them to over-ripen. Anybody ever experienced that in your kitchens? You had like a bag of mushy apples? No one's ever had mushy apples. Right. So it's really important that when you bring apples home from the store that you set them out maybe in a bowl or put them in the refrigerator, because if you leave them in a pretty sealed bag, those gases will build up and cause them to over-ripen. Which is a good thing, which can actually help you if you're running last minute on a recipe.
Is that why the bags have like the holes in them?
Yes, to let that ethylene gas out. And I think there's even green bags out there now that help to absorb that ethylene gas. I'm not sure how exactly they work, but you see produce bags are green, I think, to get rid of some of these gases. So it says this is why you can hasten the ripening of a hard avocado or kiwi fruit by putting it in a bag with an already ripe apple. An apple gives off this double bonded gas, this ethylene gas, and if you put that in a brown paper bag with a kiwi or with an avocado, it'll ripen it a lot faster. Ethylene produced by the mature apple increases the rate of ripening of the other fruit. The organic compound methanol, and that's the compound we burned yesterday, that was sample A that was sitting up here, also known as methyl alcohol. And why does it have the prefix meth?
Oh, because it's the first, because one time in your hook.
Right, one time on meth will get you hooked, and that's how you remember that any molecule that only has one carbon in it has the prefix meth. So this has how many carbons in it? One, meth. And the ending "-ol" is for an alcohol, so that's why it's called methyl alcohol or methanol. So it's very systematic how we name these compounds. This molecule contains an oxygen atom, and the structure is drawn. It's the third one down here. Right there. So that's methyl alcohol. That's the compound we were burning yesterday. Here, the oxygen atom has two single bonds, one connected to the carbon atom and the other to a hydrogen atom. So that would be another important note to put down in your notes at the beginning. Carbon always forms how many bonds? 4. Oxygen always forms how many bonds? We just got done reading. It forms how many bonds? Here, oxygen atom O has 2 bonds. And the reason for that is it's in column 16. It has 6 valence electrons. How many bonds does it need to make so that it can get to 8? 2 more. 1, 2. So it forms 2 bonds because it already has 6 electrons. So atoms are trying to get to 8 electrons. So it's however many they start with. You keep adding bonds until it gets to 8. As always, carbon has a total of 4 bonds. In compounds where there is a double bond between a carbon atom and an oxygen atom, for example in acetic acid or vinegar, and we'll put that picture up here. There's our vinegar picture. And again, these are structural formulas because every single atom has been drawn and every single bond has been indicated. It's written as C2H4O2. It does not directly indicate where the double bond is. This is the reason we draw chemical structures, to show exactly which atom is attached to which other atoms and where the double or triple bonds are. We can draw these structures in an abbreviated or more condensed form. Acetic acid could also be written as, so let's go ahead and draw the condensed form. If I don't want to draw all the bonds in this CH3 group, I can just label it as CH3. You need to make the mental connection that those 3 H's are truly attached to that carbon. So find your vinegar picture. says acetic acid. Okay, and it's attached to C, double bonded to O, bonded to OH. Now some books will try to write it like this, CH3, COOH. That's really condensed. I would try to steer clear from that because by writing it this way, it's truly the same thing as this, but you're missing out on that double bond. You really want special parts to be drawn in your picture. In other words, I want double bonds to be drawn. I want OH groups to be drawn. You can kind of condense all the C's and the H's, but try not to get rid of any double bonds. You can draw it this way, but you just need to know in your head that COOH means that one of the O's is double bonded and the other one is attached like an OH. Any questions on that condensed formula? It says there are of course still there, but these shortened forms are faster to draw and just show as clearly the relationship among atoms. The system of drawing structures works well for smaller examples, but when the molecules get bigger it becomes quite time-consuming and difficult to follow. For example, let's go back to the queen honeybee molecule. So we'll go back to our queen bee. If you took the time to draw this entire molecule out, just like at the top of page 14, you would get a picture that looks like this. Right there at the top. So this is that picture that needs to go in that queen bee molecule on the first page there. Notice how every single carbon is labeled, every single H is labeled, every single O is labeled, and that's why it's called a structural formula. Everyone see where we're at? So we're back on the first page. We went back to the honeybee molecule. There's 10 carbons in a row, and some of the important, Will, you still with us? Are you guys going to be? Okay, do you need to go to the nurse to get it out? Because I don't want that splinter to distract Ruth. We know what happens when Ruth pays attention in class. She ends up getting 100%. Not a bad thing. That's definitely a good thing. Alright, so it's really important that that OH is in your structure. It's important that that double bond is there. That double bond O and that OH are also labeled. Yes, Jaden.
Wait, is this one for the honeybee queen or the honeybee?
This is the honeybee queen. Anybody need more time? Okay. It says the full structure is cumbersome to draw and looks very cluttered. For this reason, we often draw compounds using a number of shortcuts. And again, we'll see some of those shortcuts in just a second. This does not mean that those atoms are not there. We just do not take the time to show them. A carbon always has how many bonds? 4. Yes, it always has 4 bonds. So if your picture does not show it having 4 bonds, those other bonds would be to what element? It would be to hydrogen. The H's are drawn. So if we simplify this molecule, we can simplify it like this. And let's just take some time to add some detail here. This carbon only has 1 bond. So my question is, how many H's would it be surrounded by? Number 3, Kelby.
3.
It would be 3 because that would make it bond number 2, bond number 3, bond number 4. This carbon right here is only drawn with 2 bonds. So then my question is, how many H's would need to be on that one? 3. Again, and for time's sake, we're not taking the time to draw it, but there would be 2 H's on that one. Let's take a look at this carbon right here. There's a double bond on the right, and there's a single bond on the left. So how many undrawn H's are there? Kilby.
One on the bottom of that C.
Because that would be 2 bonds is the double bond, a third bond is the single bond, and the fourth bond is to that H. So you always have to know that carbon gets 4 bonds, whether they're shown or not. Any questions on that? Alright, as well, the carbon atoms are often shown joined at an angle instead of in a straight line. This is more indicative of the true shape of the molecule. In this format, the queen honeybee molecule would look more like this. And we're going to be talking, we'll do an internet activity probably towards the end of next week where we hop on the computers and actually get to rotate molecules in three-dimensional space. So this is more like the three-dimensional shape of that molecule, and it's less like a chain and it's more like a zigzag. And that's why we call it the line angle formula. So when we put that all together, this is the line angle formula at the bottom of page 14 that you guys need to draw for the queen honeybee molecule. So you want to get that zigzag pattern going. You've got 10 carbon atoms in it. You want to make sure you have the OH. You want to make sure you have the double bond where it goes, and also the COOH. And again, as long as you understand what that COOH is saying, that's fine. You can write it like that. But probably at this level of chemistry, I'd say it might be better to draw it like C double bonded to O, single bonded to OH. Again, as long as you understand COOH actually means that, but that double bonded O is pretty important. Any questions about any of the three different types of pictures? All right, let's go to the top of page 15. It says, here the end of a line in any intersection represents a carbon atom. All other atoms, except most of the carbons and hydrogens, are still drawn. So that's the important thing. We're taking some shortcuts on the C's and the H's, but we really want everything else there. By simplifying in this manner, it's really easy to see the differences between the queen molecule and the worker molecule. So these would be the line angle formulas for both the queen and the worker. So make sure you update your worker molecule picture for the line angle formula. And again, notice how they're almost identical. The OH is in a different spot. That's really the only difference. So again, if it was me learning how to draw these for the first time, I'd recognize that there's 10 carbon atoms here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when I put my pen or pencil on the paper, you just start zigzagging. So start out at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon atoms. I put the OH this time on the first carbon. The double bond goes at the bend right before the end. I add my C, double bond O, single bond OH. And that right there is the sex pheromone for a worker bee. When the queen smells a bee making that molecule, she knows it's a worker bee. All right, working backwards in your pictures, you already have the condensed formula. And again, we got those numbers because this carbon right here, it already has 2 bonds. It's bonded to a carbon up here, and it's bonded to an OH down there. So if carbon is already bonded to 2 things, how many hydrogen bonds, or how many bonds to hydrogen does it need? Melanie? How many bonds does carbon like total? How many bonds does carbon always make? 4. Okay, add that to your notes. Carbon always makes 4 bonds. Okay, it already used up one of its bonds here. It already used up one of its bonds here. How many hydrogens do we need to attach to that? 2. So again, that's why in the picture in your packet, it shows that that first carbon has 2 H's. Same thing about this carbon. This carbon has 2 bonds already, so how many H's is it going to bond to? 2. So 2 H's, 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 2 H's. That's a lot of H's. If you would like to learn a shortcut method, We can do that right now. In other words, this is a CH2. This is a CH2. That's a CH2. CH2, 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 CH2. So the question is, how many CH2s? This would be a condensed and even further condensed molecule. So how many CH2 groups do we have? 1, 2, 3, 4, 5, 6, 7. Just like in unit 1 or 2, we learned that we can put that in parentheses and put a 7 after. So I'd like you to add this to your picture on the first page here. They drew out every single grouping of atoms, but we can lump them together. By putting a 7 after CH2, we're saying we have 7 of the front. We have 7 CH2s. Let's talk about this carbon right there. So this carbon has a double bond on it and a single bond on it. So how many H's would attach right there? Number 16, Travis. If it has a double bond and it has another single bond, that's a total of 3 bonds. How many H's would it need to get to its magic number? Let me ask it this way. How many bonds does carbon always form? 4. 2 of them are in a double bond. Right there. 1 of them is a single bond. So how many more bonds does it need? Try it again. Double bond is 2 bonds. It has a single bond. That's a third bond. How many more bonds does it need? It needs 1 more. So this right here is an H. Let's take a look at this carbon down here. That one has a double bond. That's 2 bonds. It has a single bond. That's a third bond. How many H's does it need? 1. So in other words, back to back I have a CH group. So there's a CH, and I can say that I have 2 of them. And then at the very end, we have that COOH. And again, you can write it that way as long as you know that that is a double bond bonded to a single OH. So we have a condensed formula, and we have an even more condensed formula. So it just depends how much detail do you need in your pictures. All right, before we move on, did you guys take the chance to write the entire structural formula for the worker bee? All right, let's go ahead and do that right now. So in the structural formula, and I'm not going to ask you to do this often, you draw every single bond. So when it says CH2 here, actually take the time to draw C connected to 2 H's. So you're basically expanding what's already in this condensed formula. So when you're done, you can check your work with what I have up here and see if you agree. And after doing this a couple times, hopefully you can see why they came up with a lot of these shortcut methods. Double check every carbon. Does every carbon have 4 bonds? Double check oxygen. Does every oxygen have 2 bonds? And double check every H. Every H can only ever have 1 bond. based on our skeletal formula, this would really be a bent molecule or a zigzag molecule. It's kind of hard to do in this format, but that's exactly why over here we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put an OH on, put a double bond on, double bond O, OH. So again, the molecule looks more like that zigzag shape and less like a big train. Any questions on that? Alright, so let's keep working towards the middle of page 15. It says, it is now also easier to compare these compounds to those emitted by other insects. For example, bombacol, the pheromone or sex attractant molecule between the male silkworm moth, has 16 carbon atoms, as opposed to the 10 carbon atoms in the honeybee queen molecule, also a pheromone. It has 2 double bonds instead of 1, and it lacks that COOH group. So we have the picture up here, which would be what type of picture? What type of picture is this? Darian? Yeah, this would be the skeletal formula. So now I want you to work backwards and turn that into the condensed formula, and then turn that back into the entire structural formula. Draw every single bond. Now the nice thing is, in future, we're not going to draw all the bonds, but I just want to prove a point up here. Let's spot check a few atoms. Alright, this very first carbon, it only has 1 bond to another carbon atom. So the question is, how many bonds to H would it form? Number 14, Caleb P. Actually, you just got back. You definitely want to update your pictures. When you left for the bathroom, I checked your model, and you're not up to date on your models. Okay, we've been drawing, as we read this packet, you want to make sure you draw those in yours. Okay. Number 9, Melanie. This first carbon only has a line attached to it. So how many other bonds does it need? 3. So for your condensed formula, there would be a CH3. There'd be 3 H's on this carbon. Let's take a look at the next carbon. The next carbon right there has 2 lines attached to it. So how many H's would that be? Number 6, Steph. That would be 2. So the next carbon would have a CH2. Well, let's take a look at this next carbon. That has 2 lines, so how many H's does that get? Johanna? 2. So we could actually put this in parentheses and say we have 2 of those CH2 groups. You could actually write it twice if you wanted to. I'm just trying to condense things a little bit. As far as this carbon, it has a double bond on the right and a single bond on the left. So how many H's haven't been drawn? Steph? 1. So that would be a CH group. Well, what about this carbon right there? It has a double bond on the left and a single bond on the right. Number 13, Kim. Okay, let's take a look up here. Do you see the carbon I'm pointing at? It has a double bond on the left and a single bond on the right. How many bonds is that? 3. How many H's haven't been drawn? Carbon always likes how many bonds? 4. How many does it already have? 3. How many haven't been drawn? 1. And that's to what element? H. So in other words, we have another CH group. So I could put a 2 after that. I'm going to hold off on doing that because if you take a look at the next carbon, it has a double bond on the right and it has a single bond on the left. So how many H's does that get? Number 12, Jaden.
Wait. I'm certain there's a
Okay, do you see this carbon right here?
yeah.
Okay. Do you see how it has a double bond on the right? 2 lines off to the right from it?
Yeah.
Okay, and do you see how it has a single line on its left?
Yeah.
How many bonds haven't been drawn? 1. So that's another CH group. And the same thing applies right here. So if we count up all those CH groups, we have 1, 2, 3, 4 of them. I could put that as a 4.
Okay, but so does like I don't understand.
You're so close.
Because like
Yeah, get that question out.
okay, So since there's the double bonds, does that count for like each one that's like on the
Right.
side?
In other words, this carbon right here has a double bond on its right. This carbon right here has that double bond on its left. That double bond counts for both atoms.
Okay, and then when we were doing the other thing, how it's like going up, I didn't understand that either. Like, how do you know that there's
3 H's attached to it.
yeah?
Okay. So let me just put a dot on that carbon right there. Do you see how it only has one line sticking to it? Like this line right here. It only has one line coming out of it.
Yeah.
Okay? Carbon needs how many lines? 4. So where did the other 3 come from? The H's.
Okay.
Does that make sense?
Yeah.
So we're taking the bare bones, the skeletal formula, and now I want to work backwards and just make sure that you understand what hasn't been drawn. So you got to be able to go both ways. Take the detailed picture and simplify it, and take the simple picture, and I got to make sure that you know what's going on behind the scenes. Does that make sense?
Yeah.
Okay, let's keep working our way down the line. Literally. The carbon that I just pointed out has how many bonds? Hold up the fingers. That dot that I just put there. How many lines is there? Okay, so then hold up the number of fingers for how many H's it would have. Good, I see 2 H's. So this is a CH2. 1, that's a CH2. 2, that's a CH2. 3, that's a CH2. 4, that's a CH2. 5, and you get a CH2. 6, and you get a CH2. 7, and you get a CH2. 8, and you get a CH2. 9. There are 9 CH2s up there. Do I want to draw all of them? CH2, 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 CH2? No, so I'm just going to put CH2 with a 9 after it. Whew. Any questions how we got that? So once you figure out 1 or 2, you can keep working your way down the line if you see something that looks very similar. And what's hooked on to the very end of it? An OH. Which makes you think it's what type of compound? OH. Yes, that is an alcohol. Just like all of those chemicals we were burning the other day, they were alcohols, they had OHs, this would be an alcohol. Alright, if you haven't already taken the time to draw the entire structural formula for this one, this is the longest one, take some time right now. I'll put the picture up here, I'll probably go to a clear screen, that way I have plenty of space to draw it. I know it's a little cramped to fit it in there, but just draw little C's and little H's. Okay, now you're drawing every single bond. Is anybody's eyes going cross? 2, 3, C, 4, 5, 6, 7, 8, 9. Double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons. All right, now fill in all the H's. Whew. When you are done, double check. Does your picture have 4 lines on every carbon? Whew. And let's just say if you were a female silkworm and you got a whiff of this, this would be untouchable. Yeah. Yes, this is the complete structure form.
I lost count of the C.
Okay,
I don't know.
what do you mean just lines?
Like the C's. She means like put like the C's in a row and then like.
Okay, good point. So depending how much detail you want, if you decided to put all your C's in a straight line, totally fine. But do we see why this might be a better one because it's the three-dimensional shape? Yeah, if you did it all in a straight line, your eyes probably aren't crossed right now and you're probably not having a seizure. Totally fine if you put it in a straight line. Do we see how this has more detail then? So it all depends how much detail are we looking for. Do you see why chemists came up with shortcuts? I would much rather go like this. 1, 2, 3, 4. Double bond. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Add in a few O's and double bonds here and there. And yay! And we're done. Alright, we gotta keep going. It says, it is particularly useful to leave out many of the carbon and hydrogen atoms when dealing with what are called cyclic compounds or circular compounds, a fairly common structure in which the carbon atom forms a ring. The following structure represents the molecule cyclohexane, so find that one in your packet. Cyclohexane. And I've already drawn all the C's and the H's for you. Now let's go backwards and let's figure out what the condensed formula would be. You could say CH2 is attached right there to a CH2, which is attached 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 to a CH2, and yay, we have a six-membered ring. That's where the hexane comes from, except it's circular, so we call it circular hexane or cyclohexane. And if you really want to draw a quick cyclohexane molecule, you go like this. 1, 2, 3, 4, 5, 6. If you were in geometry class, you would think that that is a hexagon. And again, if you took the time to draw it out, this is what it would look like, but hopefully you realize that this takes a lot less time. As long as you understand each one of those carbons has 2 bonds, so therefore each carbon has how many H's? Well, these carbons all have 2 bonds, so how many H's are magically there behind the scenes? 2, because 2 bonds and 2 H's gives you 4. Any questions? Alright, you might actually need this next molecule after all these chemical structures. As you can see, when we put in all the bonds and write in all the atoms, the resulting diagram can be confusing. If you find yourself getting depressed, you might need some Prozac. The fully drawn out version makes it really hard to see the structure. So here's the entire structural formula for Prozac. That's the antidepressant. This is horrible? Yes, okay. Now, so the nice thing is you don't have to draw this picture, we just need to simplify it a little bit. And you'll notice that even this carbon atom hasn't been drawn. They didn't actually draw in a C. They were finding it pretty difficult to get all these atoms in up here. So again, at each one of those places there would be a C. Let's skip right to the skeletal formula. Okay? So I need a ring that has 6 sides to it, so draw a hexagon. It has a double bond on the sides, kind of alternating. We have a CF3 on this side. I'm not going to take any time to draw any of the H's. I put an O that goes up, and then it goes back down. This carbon right here is attached to another 6-membered ring, which has double bonds on it. And then I go up and down. Again, I'm not going to draw the C's. And then when I go up, that's an N. I should probably draw that because that's one of the special atoms. And then I go to a CH3. So that takes a lot less time to draw. And it's the same thing as this, just without all the H's. So 2 circles. So when you get your final picture, hopefully it looks like at the bottom of page 16 there. You've got 2 circles, you've got a CF3, an O connecting them, a zigzag, an NH, and a CH3. Alright, chemically speaking, an aromatic compound often does have a smell, although not necessarily a pleasant one. The word aromatic, when applied to a chemical, means that the chemical contains the structure benzene. And this is one of our last pictures up here. So that 6-membered ring with all those double bonds was actually this benzene ring right there. And again, they didn't take the time to draw C's at all these different points. There'd be a C at all of those. So when you really simplify it all the way over here, you simply, for a benzene molecule, you get a hexagon that has double lines every other bond. And if you wanted to do a condensed, you could go CH, 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 there, with double bonds every other one. So again, hopefully what you've realized as we've read this article is you can have lots and lots of detail in your picture, and you can have a little bit of detail in your picture. We can go with the least detail as possible as long as you know what shortcuts we've taken to get there. Any questions? So just go back.